So I do want to start with just what is biofeedback. And in fact, biofeedback is really something we engage in pretty much every day. So generically, biofeedback is the use of some kind of a technology to give us information about our biology, the biofeedback part, that we otherwise would not be able to have. So while we may generally know how to put makeup on or brush our hair, it really does help to have a mirror. Or while we may feel ill, we don't really know what our core temperature is without a thermometer. And then we take that information and we do something with it. So clinically speaking, biofeedback is really about getting that information we can't otherwise have access to and then using it to improve health or performance. A little more technically, when I talk about biofeedback in the clinical setting, it uses instrumentation to reflect real-time physiologic information that it wouldn't otherwise be available. So again, we don't really know what's going on in our brains. There is activation there, but I can use sensors to reflect what's going on in real time. And then we use that information to make some sort of physiologic adjustment. So for example, if somebody has attention deficit, they'll often show really strong, sort of too strong, slow brainwave activity. So I might want to calm that brainwave activity down, but bump up some faster activity. Now, biofeedback is a training model. So it's not, I don't know what sort of experience you've had with psychotherapy or what you might imagine it's like. It's not traditional psychotherapy. It really is a training model where I'm setting up certain conditions that I want your physiology, I want to shape your physiology in a particular direction. And then finally, one of the things that attracts me to biofeedback is it really exists in the interaction of the biological and the psychological. So I'm a psychologist, but I have a lot of physiologic background and medical background. So I'm really interested in that mind-body connection and utilizing that mind-body connection to improve health. Now, one way we can think about the body is as an incredibly complex machine. And it's a machine that includes all sorts of very, again, complex systems that not only have to work well, but have to interact well. And it has to do this in the context of multiple, almost countless changing environmental, both external and internal variables. Even walking up the stairs requires an enormous amount of physiologic adjustment. Now, we don't think about that. If we did, we would not be able to move. It's all done automatically, sort of subconsciously, if you will. And so if you just think about the body from a mechanical perspective or a functional perspective, you can think of it as a series of interacting systems. And the way that these systems keep the body in a viable range typically is through being split into opposing halves. And so one of the sort of most, easy to understand and most important systems is what we call the autonomic nervous system. So the autonomic nervous system is the part of the nervous system that drives all of our automatic functions, our organs basically, anything below the neck. And it's divided into two halves that act in opposition. There's the sympathetic side and the parasympathetic side. So these two sides, again, they interact to maintain our organs within viable range. So our hearts don't beat 300 times a minute, and they don't stop. They're kept in range by this sort of changing or alternating influence of sympathetic and parasympathetic activity. And in fact, if you looked at heart rate in real time, it varies constantly. So, most of us have taken our pulse, for 15 seconds or a minute. That is an average. Heart rate is always changing, and it can reflect the neural influence on its activity. So as heart rate increases, we know that that's because the sympathetic nervous system is increasing in influence. And when heart rate decreases, we know it's because the parasympathetic nervous system is increasing in influence. Now, the way that the body decides how much influence, how much to move, how much influence to include how to shift organs so that they are viable and adaptive is through a series of physiologic feedback loops. So the body itself includes lots of feedback loops that give information, send that information to a control center, usually the brain, and then that control center makes changes as necessary. So, for example, blood pressure is a pretty important and relatively simple, relatively being the keyword, feedback loop. So the information from blood pressure is picked up by baroreceptors. These are stretch receptors that are in the arteries. And that information is sent on to an area of the medulla oblongata, which is in the brainstem, old brain, which controls blood pressure. And then based on that information, those centers change heart rate or blood flow. If you want to reduce blood pressure, you slow your heart rate down, or you open up your blood vessels, reduces pressure. So, for example, if blood pressure is high, that information goes through to the medulla oblongata, realizes blood pressure is out of range, and then changes heart rate, slows it down, or dilates arteries in order to reduce blood pressure. Once that information, once it's back to normal, the medulla oblongata basically says, okay, we don't need to do anything too special right now. Now, we can sort of take this model and apply it to the brain more directly. The brain's feedback systems are a whole lot more complex. And by complex, what I mean is there's rarely just one feedback system. All of the elements of the feedback system are influenced by multiple feedback systems. They all connect both directly and indirectly to each set. But to oversimplify, this is a representation of one feedback system or neural circuit within the brain. And this neural circuit includes the prefrontal cortex, it's basically the front of the brain, which is involved in determining what something is and what to do about it. Now, it sends that information to a part of the brain which is down the midline called the anterior cingulate, well, the cingulate, particularly the front of the cingulate, the anterior cingulate. And that part of the brain sort of decides, how do I feel about this? So that part of the brain is involved in reward and pleasure and deciding if something is finished. And then further, the anterior cingulate then sends that information to the thalamus, which the thalamus is basically a relay station. Sensory information goes to the thalamus, and then the thalamus decides where that sensory information should go. So, for example, supposing you realize that your hand is dirty. That information is picked up by the prefrontal cortex. My hand is dirty. Sends that information to the anterior cingulate, doesn't like it. It sends that sort of not liking it information to the thalamus. The thalamus decides we've got to do something about it. Focus on the dirt. Prefrontal cortex says, wash the hand. So you wash your hand, cleans up. Prefrontal cortex says it's clean. Everybody else is okay now. So that's a pretty typical oversimplified model of how the brain decides something, decides on an action, and then realizes the action's done, is fine. Feels good about that. Now, it may happen that there's bad information from the prefrontal cortex to the anterior cingulate. So it's not quite sure what's going on. So it gets a little nervous. And furthermore, that information may be a little fuzzy to the thalamus. And so there may be a little anxiety. So the hand's washed, it's clean, but since the information's dirty, the other brain's not quite sure it is. So it repeats the action. So wash the hand again. Now, this is a pretty normal behavior. You've probably all checked something even though you kind of knew it was done, but you're like, it doesn't feel like it, I gotta check. That anterior cingulate decides things if something's finished both cognitively and emotionally. So you kind of may know it's done, but if you don't feel like it is, that generates a little anxiety. And the purpose of anxiety is to make you do something to get rid of the anxiety. So you wash your hand again. You check your keys a second time, even though you know you did it. So like for me, I'm always checking hotel room keys, those little key cards. When I leave the door, I'm always checking, even though I know full well, one, it's in my pocket, two, even if it's not, I can go get a new one. But That's my way of putting it. However, there are times when that circuit is really dirty. And so, washing the hand, prefrontal cortex knows it's clean, but the rest of the system doesn't, and repeats it. And it may repeat it again. And again. Thus, a compulsion is born. So when we talk about OCD, obsessive compulsive disorder, what we're really talking about is bad brain circuitry, particularly the anterior cingulate. It doesn't know something is done. It doesn't know it's finished, not sure. So it kicks in some anxiety and forces the thalamus to hyper-focus on the problem, the obsession. I'm obsessed that my hands are dirty. And since it doesn't feel done, the anxiety drives me to wash my hands over and over and over again. Now, what biofeedback or neurofeedback in this case would do is try to support parts of that circuit to build up the efficiency, to clean up the circuitry, to strengthen the problematic information movement. Now, it may do that by strengthening activity, by weakening activity we don't want, or by improving communication between sites. Now, for OCD and neurofeedback, we typically would try to work at the anterior cingulate, because there's often either too much really fast activity, so it's sort of hyperactive, and in fact that circuit is hyperactive in OCD, or there's just really mushy, slow activity, so information can't really move through it. So in neurofeedback, we can kind of train that back towards a more usable, typical, normal, in the statistical sense, activity. Now, neurofeedback and biofeedback in general, people tend to think of it as a relaxation technique. And that bothers me for a lot of reasons, which I won't get into now. I won't get on that soapbox. But really, technically speaking, and more accurately, I'm not talking about relaxation. I'm talking about self-regulation. Particularly with neurofeedback, I'm not just trying to down-regulate things. I'm not just trying to get the brain to relax. I may be up-regulating. In fact, there's a lot of brain issues where I want to up-regulate. For example, in OCD, I may need to up-regulate. For attention deficit disorder, I will need to up-regulate. For peak performance, the definition of peak performance is to up-regulate. But I'm not just up-regulating either. I'm really improving self-regulation. So with something like peak performance, I want you to push that activity up, but I want you to be able to decide when to do that. So it needs to be appropriately rapid. A good example is tennis playing. So tennis is a game in which there are explosions of action. And those explosions of action need to be timed accurately. So it's not just activation all the time. It's activation and deactivation and building the skill to do that. So really in biofeedback and neurofeedback, what we're trying to do is help the systems better self-regulate. So this is, as I said, it's a training model. And what we do is we train systems, we reward them as they move in the direction of activity that we are interested in. We shape that behavior. So anyone's ever trained a pet or other animal? It's kind of like the same model. If you're training a dog to come to you, you just can't reward them to come to you. They don't understand the behavior. But if they move towards you, you give them a treat. Next time they move towards you, you give them another treat. And then you kind of like want to go for those treats. So you're shaping the behavior. And then you make a little more demand. And so then you don't give them a treat until they come close enough to touch. Over time, you shape the behavior. And then you say to them, they come over, and then you say, come. So then you're connecting one totally incomprehensible word, or sound, not even a word to a dog, to the behavior. And eventually they learn to associate the sound to come to coming over and getting a little reward. So we shape successive approximations. We ignore what we don't want. So if you want the dog to come and it sort of comes halfway and then walks away, you don't do anything. Now, we can talk about punishment, but I don't do that in a clinical setting. There's actually argument that ignoring things is experienced as punishment, but we're not punishing brains. And then finally, you got to practice it a lot. So again, if you've ever trained an animal, it takes a while. It takes a lot longer to train neurons. So this is work, like any training. What exactly is neurofeedback? So I'm going to get a little bit more specific at this point. It's high tech. It uses all this equipment. I'll show it to you when I'm done talking. But really, at the end of the day, it's a training model. We are training neurons. So, neurons. Neurons are basically cells that transmit information. They are the body's communication network. And there are lots and lots and lots of them. By the time you're 25, you have about 100 billion neurons in your brain, hopefully. And each neuron can connect up to 200,000 other neurons. So you have a quadrillion or 10 to the 15th connections in your brain. So it is an incredibly complex machine. It's a big information processor. It likes information. It likes to gather information and likes to figure out what it means and what to do about it. And, at some level, if you just sort of think about it from an evolutionary perspective, you better know what's going on out in the world or it's going to kill you. So it's gathering information, trying to figure out what to do with it. Now, it does this in an electrochemical fashion. And by that I mean there are chemicals within each neuron called neurotransmitters, do what their names say, which create an electrical signal that travels from neuron to neuron. And basically the way that works is neurotransmitters respond to voltage. They're stored at the far end of the neuron, down here in the axons. And as they're electrified, they are released by the axons into a space called the synapse between cells. It's picked up by the next cell along the line, and as those neurotransmitters accumulate, the electrical potential, that is the potential for an electrical current or an electrical signal, grows. Some neurotransmitters increase that, they're excitatory. Some neurotransmitters decrease it, they are inhibitory. But eventually there's enough of an electrical potential that the signal is sent down the cell to the neurons in the next cell, to the neurotransmitters in the next cell, which are then released when they're electrified and continue the signal down the chain. Now we can pick those signals up. Basically, it's voltage. When we look at what that signal looks like, this is voltage across time. So that voltage is always changing. Now, it is similar, if anyone's ever looked at, voltage from the power outlets, it is a sine wave. It cycles 60 times a second in the United States. That's why we talk about things that have 60 hertz. Hertz is cycles per second. In most of the rest of the world, it is 50 hertz, 50 cycles per second. It's not so normalized or regular in the brain for hopefully obvious reasons, but it's still cycling. And we can take that information, we can take this signal, and we can break it down into component frequency bands. And when people talk about brain waves, they're talking about electrical signal that moves at different ranges. And I'll talk a little bit more about that. But where is it coming from, the signal that we're collecting? The brain is pretty big. Well, since we're putting the sensors on the scalp, I'm not inserting electrodes into the brain. We're really just picking up signals that are coming off the outer layer, the cortex, the cerebral cortex. And that's a layer of cells, of neurons. It's about 3.5 to 5 millimeters thick. And what we're getting really is just signal that's leaking out. Signal always leaks out. If I took a very sensitive voltmeter and put it near an outlet, I would pick up electron flow, electricity. Same thing with this. So we're picking up the signal that's leaking out of the brain. And because we kind of know functionally what different areas of the cortex do, we can focus on areas of interest. So, for example, this is Wernicke's area and the Broca's area. Those are areas, typically on the left side, that have to do with speech comprehension and speech production. So if someone has aphasia, that is inability to speak perhaps from stroke or something else, we may be able to build up their activity using neurofeedback. So the modularity of the brain, the cortex is pretty modular. It's not exact a one-to-one map, but it's pretty modular, and that allows us to sort of figure out where we want to train based on what we're trying to change. Now the cells, the particular neurons on that cortex are what we call pyramidal. That is, they're called that because they are shaped like pyramids. They go deep into the brain. So even though their ends are what make the cortex up, the bodies and the axons go deep into the brain. So even if we are talking about changing surface neurons, there's a cascading effect in deeper areas of the brain. So the training we do is not just in a local area. These neural networks and neural circuits interconnect and influence each other. So measuring brain activity basically uses an electroencephalograph, EEG. It is just a glorified voltmeter. And we've been measuring electrical output of the brain for over 100 years. It was Hans Berger in 1924 measured the first human EEG. And by the early to mid-60s, we found that organisms could be taught to generate desirable brainwave activity. So Barry Sturman, University of Los Angeles, University of California in Los Angeles, he did a lot of work on perception and trained cats. He was doing a sleep study. So he trained cats to recreate a type of brainwave activity that's often seen in sleep, but to create it while awake. And this is the brainwave activity that goes across the middle of the brain in the juncture between where the sensory and the motor, they come together in what's called sensory motor cortex. So he trained cats to generate this sensory motor rhythm, SMR. Then he finished the study, and he was then contracted to do a study for the military to see what were the effects of low exposure to rocket fuel. This was for pilots. Concern was, we knew lots of, high dosages of rocket fuel would kill you, but, what were low dosages do? So he took the cats and he exposed them to low levels of rocket fuel and measured how long it would take them to start to seize up and die, which is what will eventually happen to you. The cats that had been trained to create this SMR rhythm didn't die. They didn't seize. So what he had inadvertently discovered was that by training up the sensory motor rhythm, you could create resilience to seizure. So he thought, that's interesting. I wonder if it works in people. He just happened to have who had refractory seizure disorder. So this was somebody who'd been on medications that weren't working, had high frequency of seizures. So he trained her to create the same rhythm over the sensory motor strip. And within 2 years, she was seizure-free, never had a seizure again for the rest of her life. It was the first clinical use of neurofeedback. So now, when we're talking about neurofeedback, we are using EEG. This is, during the 70s, neurofeedback kind of got connected to counterculture and sort of certain practices that led to it being sort of not taken seriously, shall we say. But it really draws from well-established neurology. It really is it's a clinical use of neurology. And so we use the same nomenclature and the same approaches as neurology would. So, for example, This is called the International 1020 system. It's where we place sensors that is agreed upon worldwide. And it's called 1020 because it's based on distances the size of the head, and the distance either 10% or 20% from the edges of the scalp. There's now a 1010 system, so it's just 10%, that allows more sensors. And in fact, I think there are now cascading sensors. You can over 1,000 sensors now, individual sensors. We don't use those clinically. That's really research grade. But basically, most people clinically are using this 1020 system. So up to 19 sensor placements, although people will place in between as well. So basically, when we measure, we are measuring the electrical activity. And as I said before, we can take that electrical raw activity and we can break it down into different bandwidths. And these have been named, delta, theta, alpha, beta, gamma. They're not in order. That's because alpha was discovered first. Then we didn't have the technology to measure slower. So they're not in speed order. They're in order of which of discovery. So delta, I just want to go quickly through. Delta is the slowest. In adults, it's found during sleep. If you have a lot of delta when you're awake, you have a head injury or some sort of disease process going on. Theta, fairly slow. It's 4 to 8 hertz. That is 4 to 8 cycles per second. And theta is found when resting, during periods of creativity or meditation. But it also can reflect inefficiency. So individuals who have attention deficit have excessive theta in their frontal lobes usually. Alpha is the idling speed of the brain. So there's a lot of alpha, and that kind of is, we take a look at alpha and we kind of can use that as a basic idea of how efficient the overall brain is. So it's a lot of alpha when you're awake and relaxed. But it also can reflect, if there's too much of it, it can reflect underactivation. So you see a lot of alpha for depression, sometimes for anxiety, because it's reflecting underdeveloped ability to communicate information. Beta is further broken into subscales, and it's sort of the activation part of the brain. So it may reflect problem solving, it can reflect paying attention, but too much too fast can also reflect anxiety, agitation, action. And then finally, gamma we know less about. It's relatively recently kind of defined. It seems to be related to consolidation of memory. It probably has some role to play in attention. Maybe meditation. We're not entirely sure. Now the point of this, one of the points I'm trying to make is that there are no bad brainwaves. There are no good brainwaves. It has to be understood in context. So, for example, in an infant, we'd expect a lot of delta activity when that infant was awake. But when that infant goes and ages to age 12, we would not want a lot of delta in her awake state. So, what we're trying to do is not say that we need to just get rid of delta or get rid of that theta, but we need to understand it in the context. And because we have some understanding of brain activity, we can start to look at different areas and make good, educated guesses about what we would need to increase and what we would need to decrease. So, one way to start to do that is we know there are hemispheric differences. So left hemisphere tend to be spoken in written language, sort of more logical reasoning. Right side tend to be more emotional, interpersonal information, creativity. So if we're interested in somebody who's having problems processing language information, we're probably going to be somewhere on the left. Maybe the center, but somewhere on the left. And in fact, we know enough now that we kind of know general patterns that show up for different conditions. So ADHD, lots of frontal theta, slowing. The frontal lobe is all about figuring things out, trying to make your way through the world. If it's not effective, you won't know what to pay attention to. Depression, that's often real strong slowing in the frontal left. Anxiety is here. So anxiety will have sort of high beta in different areas. So we kind of know what to expect. So when we set something up, our training conditions usually want to decrease something and increase something else. And the truth is you can have anywhere from 1 to dozens of conditions. But typically we want to decrease one and increase another. Or decrease 2 and increase 1, something like that. So with this model, we want to decrease theta, we want to decrease slow activity, increase low beta, and we're putting the sensor kind of right in the center of the brain. This is a pretty standard protocol for a lot of different things because this low beta, that SMR, that sensory motor rhythm, is a very important regulating rhythm that occurs here in the center of the brain. And so increasing that while decreasing slow activity increases general brain efficiency. So we run it, we're taking the sensor, and if our beta increases, our theta decreases, we reward the brain. Now by rewarding the brain, a reward for the brain is not the same as we would think of as a reward, because we're not talking about conscious understanding, we're talking about cells, neurons. But these neurons are information processors. They like information. So they'll orient towards interesting things. And so we give them something. It could be a tone, it could be a little picture, it could be a game, points in the game. It doesn't matter as long as it's interesting. And then we ignore when things go the way we don't want them to go. And so over time, the neurons will recreate the conditions that bring them that interesting information. Successive approximations for shaping neural behavior. This is a typical training screen. So this is an animation that serves as the reward. These 3 columns are the brain waves that I wanted to change. Again, this is a pretty typical one where I want to decrease really slow, decrease really fast, and increase sort of in the middle. I set criteria for what that means based on the person's activation. And when all 3 of those things match at the same time, this animation will move. So over time, that animation will move more and more, so I'll tighten the criteria up a little bit. Again, trying to shape that behavior. Now, I said before that we know certain conditions exist and tend to show signatures. So this is depression. This individual is depressed. He's got strong, slow activity in the upper left. So we put a sensor right there, and we try to decrease really slow activity and try to move that person more towards a more normal brain. As that happens, their mood should improve. Because at the end of the day, from a clinical perspective, that's what matters. Now, for peak performance, there are a few general approaches for neurofeedback. So first we might try to improve just general efficiency, and that's typically done along the center of the brain. Again, because those parts of the brain are interconnected to both cognitive and emotional parts of the brain. And we want to really get that efficient. We want to build the efficiency there. We may want to improve the ability to calm, and that's typically going to be either in the posterior part of the brain or on the right, center right. And these are areas of the brain that are involved in anxiety. So for example, somebody who has post-traumatic stress disorder will show a lot of dysregulation in the posterior, which may be related to flashbacks, for example, or maybe why flashbacks occur. Dysregulated, because the back of the brain is also visual areas. And then we may want to reduce distractibility, and typically that's going to be in the center and the front parts of the brain. So, if somebody came in and said, I want to start peak performance training right now, here's what I'm like, I want to start today, I'd probably start in one of those 3 places. So, for example, this is neurofeedback findings from this 18-year-old pianist. She was trying to get in conservatory. She was not having any success, although she was highly skilled. Her teacher didn't think she would ever have a career. Comes from a musical family. Couldn't perform. Couldn't do it. So the type of treatment I engaged with her was based on a protocol for improving musical performance. And it is posterior. I was trying to actually increase that theta, the slow activity, because that's a creative state. It's also a calmer state. What I'm trying to do here is increase this blue, that's the theta, while decreasing slightly faster theta alpha. And I do that by reinforcing the theta across time. And particularly where you see the theta get higher than alpha, that tends to be a state of real calm, suggestibility, creativity. And so what happened here, what's interesting is the theta didn't really increase, but the alpha decreased. We're often interested in ratios rather than just pure numbers. Because it's really the interaction of the areas of the brain that we're interested in. Now, interestingly enough, this is beta, high beta, which is associated with anxiety in the posterior. I didn't do anything with that. I just looked at it. It decreased. So even though I was not focused on beta, I wasn't rewarding it, I wasn't ignoring it, it did decrease. So this is 30 sessions. So this is not fast. But she got in the conservatory. Now, supposing somebody came in and said, this is what I want, but, I'm not sure the best way to go, and I can make guesses, but I'm never entirely sure. There are ways to do a whole evaluation or brain map. These are called quantitative EEGs. And what it does is a full cap, that's me getting one in a workshop. Full cap, it's measuring at 19 different sites activity, and then it compares that activity to a normed database. So I can tell how deviant is my activity from normal. And I can also look at how do the different areas interconnect. So this is a quick and dirty one that I had done. I was doing this workshop this past spring. One of the things I want to point out on this, I don't know if you can kind of see this. Do you see that big red splotch? And there's this little red splotch on the upper left. That's a concussion I had over 10 years ago. So I was concussed when my daughter bashed into my head. Nothing showed up on MRI, but I had migraines pretty consistently for about a year. About between 6 and 12 months after the concussion, I had a full QEEG done, and it showed that. So one of the cool things about QEEGs is it can really show something that's very idiosyncratic, and that does not show up on more typical scans. So the power of this QEEG is that it really allows us to personalize our treatment. So for me, I probably would not want to increase beta, because this is beta, and it's already probably too high. It's just dysregulated. Now, one of the things we can do is we can look at multiple sites at the same time, or we can train multiple sites at the same time. So the girl who was the pianist was one sensor on the back of her head. But we can do up to 19 at the same time. And that allows us to do some interesting things. First, it's just efficient. I can train multiple sites at the same time. But also, because we're talking about a sphere, I can use telemetry to make estimates about what's going on deeper in the brain and indirectly train deeper brain structures.